Okay, let's try and wrap our heads around this. Imagine, right, you've got these two tiny, tiny bits of stuff. Particles.
Uh-huh. The smallest things imaginable.
And they, like, interact somehow. Then you fling them apart, way apart, opposite ends of the galaxy even.
Light years apart, yeah.
Now, here's the weird bit. You measure one particle, maybe see how it's spinning or wiggling, whatever.
You make an observation, yes.
And instantly, like instantly, the other one, the one that's galaxies away, it starts doing the exact opposite thing. Instantly.
That's the essence of it. They're linked.
It's like they're texting each other faster than light.
This is quantum entanglement.
Yeah. And our sources call it the most mysterious link in the universe. They're not wrong, are they?
No, it definitely has that almost unbelievable quality. But, you know, it's real. It's been tested, proven in labs. It really does mess with our everyday common sense about how things work.
Totally. And the implications for technology, for understanding reality.
Wow. Huge implication.
So, all right, if you're listening, buckle up. We are diving deep into this today. We're going to try and unpack what entanglement actually is.
And how we got here.
Yeah.
From Einstein being skeptical.
Right. His whole spooky action thing. We'll get to that. We'll look at the journey from like a theoretical puzzle to actual tech being built.
And maybe touch on some of the wilder future ideas, too.
Oh, absolutely. We have to. It's part of the fun, isn't it?
Definitely. So where do we start? To really get entanglement, you first need to grasp another quantum oddity. Superposition.
Ah, yes. The being in multiple places or states at once deal.
Exactly. Think of a normal light switch. It's either on or off. Simple.
Binary.
But a quantum particle, like an electron, before you measure it, it can be both spin up and spin down at the same time. It exists in a superposition of those states.
Like it hasn't made its mind up yet?
Sort of.
Yeah.
It only chooses a definite state, up or down, when we actually perform a measurement. Until then, it's in this kind of fuzzy probabilistic state.
Okay, got it.
Yeah.
Superposition. Quantum, maybe. So how does that lead to entanglement?
Well, entanglement happens when you link two or more of these particles. Maybe they were created together or interacted very closely.
The quantum high five we mentioned earlier.
Huh. Yeah, something like that. They become linked in a way that means they share a single quantum state. You can't describe particle A on its own anymore, or particle B on its own.
They're a package deal, even across the galaxy.
Even across the galaxy. Their fates are intertwined. A common example uses photons, particles of light, and their polarization.
Like sunglasses, the way the light waves wiggle.
Exactly. Imagine you entangle two photons, so they must have opposite polarizations. If you send them flying apart and then measure one and find it's polarized vertically,
Then you instantly know the other one must be horizontal.
instantly, no matter how far away it is. Well, that's the core mystery.
Which brings us to the big man himself, Albert Einstein, 1935. He wasn't buying it, was he?
Not at all. He, along with Podolsky and Rose in the EPR Paradox, they looked at this and basically said, hang on, this feels wrong.
What was their main beef?
It was that instantaneous connection. Einstein called it spooky action at a distance. He deeply believed nothing could travel faster than light. Information shouldn't be able to zip across the universe instantly.
The cosmic speed limit.
Right. He favored what's called local realism. Local meaning influences can't travel faster than light, and realism meaning particles have definite properties before you measure them.
Like, the particle always knew it was going to be spin up, even before we looked. Some kind of hidden instruction.
Exactly. That's the idea of hidden variables. Some unknown factor, Einstein thought, must be determining the outcome in advance, locally. Quantum mechanics, he argued, must be incomplete if it didn't account for these.
So, he thought the theory was missing something, not that reality was actually that weird.
Pretty much. But then, the same year, Erwin Schrödinger weighed in, and he took the opposite view.
He saw the weirdness and embraced it.
Totally. He said this connection wasn't a flaw, it was a defining feature of quantum mechanics. He's the one who actually coined the term entanglement.
Ah, so Schrödinger named the beast.
He did. He argued that once particles interact like this, they remain a single system, described by one shared quantum state no matter the distance. You can't just treat them separately anymore.
Okay, so Einstein says spooky and incomplete. Schrödinger says weird but fundamental. How did they settle it?
Well, for decades, it was mostly debated by physicists almost philosophically. Then, in the 1960s, John Bell came along.
And he figured out a way to actually test it.
Brilliantly, yes. He devised Bell's theorem. It's basically a mathematical framework, he asked. If the universe does work the way Einstein thought, with local realism and hidden variables, what are the limits on how correlated the measurements of two separated particles can be?
Okay, so he set a boundary based on Einstein's common sense view.
Exactly. He derived an inequality, Bell's inequality, that defines the maximum correlation you'd expect if local hidden variables were real.
And then?
And then he showed that quantum mechanics predicts stronger correlations. Correlations that would actually violate Bell's inequality.
So it became an experimental question. Measure the correlations. Do they obey Einstein's limit, or do they break it, siding with quantum mechanics?
Precisely. It turned philosophy into physics.
And the experiments. Who did them?
The crucial early experiments were done in the 1980s, notably by Alain Aspect and his team in France. They used entangled photons.
And the results?
Drumroll. The results consistently violated Bell's inequality. They matched the predictions of quantum mechanics. The correlations were stronger than any local hidden variable theory could explain.
Wow. So score 1 for spooky action.
Pretty much. Now, those early experiments, clever as they were, had some potential loopholes, tiny assumptions or technical issues that critics could point to.
Like maybe the detectors weren't efficient enough, or the choices of what to measure weren't truly random, stuff like that.
Exactly. Things that could, in principle, allow a hidden variable theory to mimic the quantum results.
But they closed those loopholes eventually, right?
They did. Around 2015, several independent teams managed to perform loophole-free Bell tests, much more sophisticated setups, closing all the major loopholes simultaneously.
And the outcome? Still spooky.
Still spooky. The results were crystal clear. They strongly confirmed the predictions of quantum mechanics and effectively ruled out Einstein's local, hidden variable explanation.
So entanglement, this instantaneous connection, it seems to be baked into reality. It's not just a quirk of the theory.
That's what the evidence overwhelmingly points to. It's a fundamental feature of our universe.
Which is mind-bending.
Yeah.
But okay, if it's real, what can we do with it? Is it just a curiosity for physicists?
Oh, far from it. It's moving from the lab into real-world applications. One of the most developed is quantum cryptography.
Using entanglement for secret codes.
Basically, yes. Quantum key distribution, or QKD. You use pairs of entangled particles, often photons, to establish a secret key between two parties, say Alice and Bob.
How does the entanglement make it secure?
Because of that core property. If an eavesdropper, let's call her Eve, tries to intercept and measure the photons to learn the key.
She disturbs the entanglement.
Exactly. The very act of measuring alters the quantum state. Alice and Bob can then test a sample of their results, and if they don't match up perfectly as expected due to the entanglement, they know someone was listening in.
So the eavesdropper automatically reveals themselves. That's clever.
It's theoretically unhackable by conventional means. The security is guaranteed by the laws of quantum physics itself. We've seen demonstrations, like China's Micius satellite distributing entangled photons from space for 2KD.
Wow, space-based quantum codes. Okay, what else? Quantum teleportation. Are we beaming people around yet?
Not quite. That name is a bit misleading thanks to Star Trek. It's not about teleporting matter.
Okay, so what is it teleporting?
It's teleporting the quantum state of a particle. All the information that defines that particle's quantum properties.
How does that work? Still sounds pretty sci-fi.
You need 3 particles. Let's say Alice wants to teleport the state of particle C to Bob. Alice and Bob first share an entangled pair, particles A and B. Alice keeps A, Bob keeps B.
Okay, standard entangled setup.
Then Alice performs a special joint measurement on her original particle C and her entangled particle A. This measurement changes the state of Bob's particle B.
Instantly, even though Bob is far away.
The correlation happens instantly, yes. But to reconstruct the original state of C, Bob needs some classical information about the outcome of Alice's measurement. Alice has to send that to him, say, over the phone or internet.
So there's still a regular communication step involved. It's not faster than light communication.
Correct. The teleportation part is the transfer of the quantum state itself, which happens via the entanglement. But reconstructing it requires that slower classical information. The first successful teleportation of a photon state was back in 1997.
Okay, so not FTL messaging, but still cool. Why is it important?
It's absolutely vital for building things like a quantum internet. You need a way to reliably transfer quantum states between quantum computers or nodes in a network, and teleportation is a key mechanism for that.
Right, connecting quantum computers together. And entanglement is crucial for the computers themselves, too, isn't it?
Oh, completely. A classical computer uses bits, zeros or boins. A quantum computer uses qubits. Thanks to superposition, a qubit can be 0, 1, or both at the same time.
Which gives you more states to play with.
Exactly. But entanglement is what really ramps up the power. When you entangle multiple qubits, they become linked. the number of states the system can represent grows exponentially.
So 2 entangled qubits can do more than just 2 separate qubits.
Way more. An entangled system explores a vast computational space simultaneously. This allows quantum computers to tackle certain problems, like simulating complex molecules for drug discovery, or breaking certain types of encryption that are practically impossible for even the biggest classical supercomputers. Think Google's quantum supremacy experiment. Entanglement was key.
So super secure comms, transferring quantum info, super-powered computing. What else is in the entanglement toolbox?
Quantum sensing or metrology. Using entangled particles to make incredibly precise measurements.
More precise than regular methods?
Potentially, yes. Because the entangled particles are correlated, measuring them together can reveal tiny changes in things like gravitational fields, magnetic fields, or even the passage of time with unprecedented accuracy.
Applications.
Could be better medical imaging, more precise navigation systems that don't rely on GPS, improved geological surveys, maybe even detecting gravitational waves. It's about pushing the limits of measurement.
Okay, this is leading towards that idea of a quantum internet, isn't it? Connecting all these quantum devices.
That's the long-term vision, yes. A global network based on quantum principles, using entanglement and teleportation for ultra-secure communication and distributed quantum computing. Tests are already happening in some cities.
Sounds amazing. Now, let's get a bit weirder. Interstellar communication, using entanglement to chat with ET faster than light.
Ah, the FTL question again. Look, the standard physics, the no-signaling theorem, says no. You can't use the instantaneous correlation to send a controllable message faster than light.
Why not? If I measure my particle spin up and know yours is instantly spin down light years away, haven't I sent one bit of information?
But you couldn't choose to make your particle spin up. The outcome of your measurement is fundamentally random, according to quantum mechanics. Yeah. You can't force it to be up to send a 1 and down to send a 0, so no controllable message.
Okay, standard physics says no FTL texts, but are people still exploring it? Fringe ideas?
Oh, absolutely. There are always people pushing boundaries. Some speculate about using entanglement for maybe highly efficient communication, even if not strictly FTL, or exploring theoretical loopholes, but it's definitely speculative.
Fair enough. What about quantum brain interfaces? Entanglement linking minds. That sounds really out there.
That is very speculative. Theories like Orcher propose quantum effects, maybe entanglement, are involved in consciousness happening in microtubules within neurons.
But there's no solid proof.
No solid evidence right now. It's fascinating, but it's on the fringes of neuroscience and physics. If it were true, the implications for brain-computer interfaces or even brain-to-brain links would be, well, revolutionary doesn't cover it, but it's a massive if.
A massive if. Got it. And entanglement, messing with time. Delayed choice, retrocausality, the future affecting the past.
Yeah, quantum mechanics throws up some really weird stuff about time. Delayed choice experiments, pioneered by John Wheeler, show that a choice made about how to measure a particle now seems to affect what state that particle was in the past.
Whoa. Head spinning again.
And some interpretations, like the many worlds interpretation, suggest measuring an entangled particle causes reality itself to split, with each possible outcome happening in a separate universe.
Seriously, multiple universes branching off every time a quantum measurement happens.
That's one way to interpret the math, yes. And taking it even further, some theorists muse about using entanglement to maybe probe or signal across these parallel universes. But again, we're deep in speculative territory here.
Deep, deep territory. Okay, bringing it slightly back to Earth. Quantum biology. Entanglement in living things.
That's actually a growing field.
Yeah.
There's serious investigation into whether quantum effects, including entanglement, play functional roles in biology.
Like what?
Photosynthesis, how plants convert light to energy so efficiently, seems to involve quantum coherence. Bird navigation, how some birds sense Earth's magnetic field, might involve entangled electrons in their eyes. Even our sense of smell might use quantum tunneling.
Birds using quantum compasses. That's amazing, if true.
It's still being researched, but it suggests quantum mechanics isn't just for labs. It might be fundamental to life itself.
So entanglement isn't just physics, it's philosophy, it's maybe biology. It really shakes up our whole view of reality, doesn't it?
Profoundly. It forces us to question basic assumptions. Do things have properties before we measure them? What is locality? Is reality observer-dependent? Different interpretations of quantum mechanics give different answers.
Like many worlds, or the idea that quantum states just represent our knowledge.
Exactly. And then there are newer ideas, like ER EPR, which suggests a deep connection between entanglement, EPR, and space-time geometry, specifically wormholes, ER bridges. Maybe entanglement is somehow stitching space-time together.
Okay, my brain officially hurts now. Wormholes from entanglement.
It's a fascinating cutting-edge idea connecting quantum information and gravity. It shows just how deep the implications of entanglement might go.
And people all over the world are still testing this stuff, pushing the boundary.
Absolutely. Ongoing Bell tests, experiments with quantum networks, projects like the Micius satellite. It's a global effort to understand and harness this fundamental and fundamentally weird aspect of the universe.
So the big takeaway, what should we remember from all this?
I think it's that the universe is deeply interconnected in ways that defy our classical intuition. Entanglement shows us that reality is non-local, that seemingly separate parts can be instantly linked across any distance.
A truly spooky connection, just like Einstein said, but it turns out it's real.
It seems to be, yes. We've gone from philosophical debate to experimental proof to the beginnings of powerful new technologies based on this very spookiness.
And the final thought, where might this all lead?
Well, maybe we're just scratching the surface. As we understand entanglement better, perhaps it will force us to completely rethink what space, time, and reality itself truly are. We might be on the verge of a whole new picture of the cosmos.
Definitely gives you a lot to chew on. That idea of interconnectedness feels different now.
It certainly makes you think, doesn't it?
Thanks for diving into this wonderfully weird world with us. Stay curious.